Now that we're all wired up, we can add some action. When the Start button is pressed, we want to create a new sleep night and store it in the database. When the Stop button is pressed, we want to update the night with the end time. When the Clear button is pressed, we want to erase what's in the database. This can take a long time when the database has a lot of data. Imagine a few years' worth of sleep data. So, this long-running operation should run on a separate thread. And as promised, we are going to talk about threads, and to make sure everyone is on a similar page, I'm just going to quickly recap. Mobile devices have processors, and these days, most of them have multiple hardware processors that each run processes concurrently. This is called multiprocessing. To use processors more efficiently, the operating system can enable an application to create more than one thread of execution within a process. This is called multithreading. You can think of it as reading multiple books at the same time, switching between books after each chapter, eventually finishing all books, but you can't read in more than one book at the same time. You, the reader, represents a processor, and each book represents code that needs to be executed, and the act of reading each book represents a thread of execution. Now, there is a lot of infrastructure to manage all those threads needing to run, sometimes in a given order, and finish too. For example, there is a scheduler, which, as the name indicates, takes into account things such as priorities and makes sure all the threads get to run and finish. No book is allowed to sit in a shelf forever and gather dust. But if a book is very long or can wait, it may take a while before it gets sent your way. And there's this dispatcher, which sets up threads. That is, it sends you books that you need to read and specifies a context for that to happen in. You can think of the context as a separate, specialized reading room. Some contexts are best for user interface stuff, and some are specialized to deal with input-output operations. The only other thing to know is that a user-facing application usually has a main thread that runs in the foreground and can dispatch other threads that may run in the background. Now, on Android, the main thread is a single thread that handles all updates to the UI. The main thread is also the thread that calls all click handlers and other UI and lifecycle callbacks. This is why it's also called the UI thread. The UI thread is the default thread, meaning unless you explicitly switch threads or use a class that runs on a different thread, everything you do is on the main thread. This creates a potential challenge because the UI thread has to run smoothly to guarantee a great user experience. You see, for your app to display to the user without any visible pauses, the main thread has to update the screen every 16 milliseconds, or more often, or at about 60 frames per second. At this speed, humans perceive the change of frames as completely smooth. That's a lot of frames and little time. Therefore, on Android, it's essential to avoid blocking the UI thread. Blocking in this context means the UI thread is waiting, not doing anything at all, for an action to be done, for example, something like a database to be done updating. Many common tasks take longer than 16 milliseconds, such as fetching data from the internet, reading a large file, or writing data to a database. Therefore, calling code like this from the main thread can cause the app to pause, stutter, or even freeze. If you block the main thread for too long, the app may even crash and present an application not responding dialog. So we should never perform long-running operations on the main or UI thread. So what are our options? Welcome coroutines.